dedicated in the magic hour. Okay,
right. So let's begin. Today we're going to do the mechanics paper of winter 2015. And the first question is, a weightlifter performs an exercise in which he raises a mass of 200 kilograms from rest vertically through a distance of 0.7 meter and holds it at that height. And question one is, find the work done by the weightlifter. So this is work done against gravity. And when you have a work done against gravity situation, it's just mass times the gravitational constant and times the height by which it is raised. So that will be 200 g times 0.7. And if you take g to be 10, we'll get 1,400 joules of work done. And part 2 of the question says, given that the time taken to raise the mass is 1.2 seconds, find the average power developed by the weightlifter. Well, how do you find power? The formula is power equals work done over time. It's kind of just the rate of energy transfer in a sense. So you got energy, which is the work done on the top, and divided by time to give you the rate. And that will be, in this case, 140 joules over 1.2 seconds. And that's 1,170 watt. Question 2. A particle of mass 0.5 kilograms starts from rest and slides down a line of greatest slope of a smooth plane. The plane is inclined at an angle of 30 degrees to the horizontal. So let's just try to draw a diagram. So we have 30 degree here. And question 1, find the time taken for the particle to reach a speed of 2.5 meters per second. So we have our particle here, and gravity always acts vertically downwards. So we can break it into 2 components. There's one parallel to the slope and one normal to the slope. And if we want the component of gravity responsible for the acceleration, is always the component parallel to the slope. And in order to find the parallel bit, you do sine 30. So force is equal to G sine 30. And that would be equal to, that's mg, and that will be equal to ma. So a, in this case, would be g sine 30. So in a way, you are taking the gravitational acceleration to be in the direction of the travel of the particle. And so now we know the value of acceleration. We would like to know how long it takes for it to reach 2.5 meters per second. So the formula would be 2.5 equals 0 plus AT, and we can work A to be 5, and T would just be 0.5 seconds. Now, when the particle has traveled 3 meters down the slope from its starting point, it reaches rough horizontal ground at the bottom of the slope. The frictional force acting on the particle is 1 Newton, so there's a horizontal ground where there's a friction opposing the motion. And we want to find the distance that the particle travels along the ground before it comes to a rest. And for this question, we would need to use Suvat. And well, this is the first method and probably the most intuitive one, where you use v squared equals u squared plus 2as. And because we want the distance traveled before the particle comes to rest, the final velocity would just be 0. And the initial velocity is just 2. Wait. So actually, the first step you need to do is to find the final velocity of the particle traveled after 3 meters. So we still use the same formula, but in this case, we're trying to find out v, the speed of the particle at the end of the slope. So that will be 0 plus 2 times 5, as we've worked out before, and times 3 meters equals 30. Okay. And the second part would be find out the deceleration of the particle at the rough horizontal ground. And the formula would be 0.5a, that's ma, would be equal to the force, which is -1. So a would be -2. And now we use the same formula again, where we have 0 squared. So the final velocity when the particle comes to a rest is equal to 30, which is u squared, plus 2 times -2, which is the acceleration, times s, and that will give you s equals 7.5 meters. And there will be another method where you use energy conservation, where you say the PE lost is equal to KE gained to work out energy. But I think our first method is the easiest and the most intuitive way of solving this question. Question 3. A lorry of mass 24,000 kilograms is traveling up a hill which is inclined at 3 degrees to the horizontal. The power developed by the lorry's engine is constant. So here it's very, very important. We have a constant power, and it's a constant resistance to motion of 3,200 Newton. Let's try to draw another diagram. So it's inclined at 3 degrees to the horizontal. And the lorry has 24,000 G of gravity acting downwards. And in question 1, it says when the speed of the lorry is 25 meters per second, its acceleration is 0.2 meters per second. Find the power developed by the lorry's engine. We should apply Newton's second law to the lorry. So F minus 24,000 g sine 3. This is also the component of gravity parallel to the slope as we did before. So when it's parallel to the slope, always use sine. And that minus the resistance to motion, which is 3,200 Newton, is equal to 24,000. This is, again, the mass of the lorry times 0.2, its acceleration. And power is equal to F times V. And as we work out from the last question, it will be 20,561 times 25. And that will give you 514 kilowatts. And just to note here, F is the driving force. We can analyze the different forces acting on the lorry. So first, you have the driving force, capital F, that's pushing the lorry up the hill. And you have this component of gravity that's acting parallel to the slope. So that says G dash. And you also have a resistance R parallel to slope. So basically you have a situation where in the direction of motion of the lorry, there are three forces acting. So that's why you need to put all three forces into the equation for Newton's second law. So after finding the power of the lorry, we are now to find the steady speed at which the lorry moves up the hill. If the power is 500 kilowatts and the resistance remains 320 Newton, well, we should use Newton's second law again. So we have 3,200 Newton of resistance plus have gravity acting parallel to the slope, and we shall set that equal to the driving force, and that will be 115,761. We use this equation because it's an equilibrium position. So all of the driving force is balanced out by the force against the motion. And we should use the formula P equals FV again. But now we want the velocity, so V should be P over F. And that will be 31.7 meters per second. Right. Question 4. Blocks P and Q of mass m kilograms and 5 kilograms respectively. So we have P here, m kilogram, and Q has mass 5 kilogram. And they are attached to the ends of a light inextensible string. The string passes over a smooth pulley which is fixed at the top of a rough plane, inclined at 35 degrees to the horizontal. So here we have friction acting on P. So let's just see what kind of forces are acting on P. We have the component of gravity normal to the surface, so G normal, and we have component of gravity parallel to the surface, which is G parallel. And the component of gravity normal to the surface would give rise to a friction, but we do not know yet which direction the friction is acting at, because friction always acts to resist the attempt of motion. And so now block P is at rest on the plane, and block Q hangs vertically below the pulley. The coefficient of friction between block P and the plane is 0.2. So E equals 0.2. Find the set of values of M for which the two blocks remain at rest. So this question is interesting in the sense that there are two different possibilities. The first possibility, so possibility 1, well, in both cases, we're looking for limiting equilibrium. The cases where the block P is just about to move, so the force just balance out. So case 1, we could have equilibrium on the point of moving up the plane. So moving up the plane. So in this case, Q is so heavy that P is about to be pulled up by the string. And we have a second case where P is just about to move down the plane. In this case, the block Q is so light that it's about to be pulled up by the string. So let's just see how these different cases would work. First, find the component of gravity parallel to the plane. And as before, we do mg sine 35. And we also have the component of, so this is parallel, component of gravity normal to the plane, and that will be mg cos 35. And friction would just be 0.2 times mg cos 35. Okay. So in the first case where the block Q P is about to move up the plane, friction must act to oppose the motion. So Fx down the plane, and let's equate all the forces together. So the block Q would provide a 5 times G of forces, and that will be equal mg sine 35. So component of gravity parallel to the plane on P, and plus 0.2 mg cos 35, and this is the friction acting down the plane. And in the case where P is about to move down the plane, friction must act up the plane. So we're going to change the sign. 5 times G would now be balanced out by mg sine 35 minus 0.2 mg cos 35. And so for these two equations, we'll get the first m is equal to 6.78, and the second one will be, let's call it m1, and the second one will be m2 is equal to 12.2. Okay. And because these two cases are the limiting cases, the mass can take any value in between these two limiting cases. So mass is anything between 12.2 kilograms and 6.78 kilograms. Question 5. So we have a vector diagram of forces acting on a small bead Q that can freely move along a smooth horizontal straight wire AB of length 3 meters. Three horizontal forces of magnitude F, 10, and 20 act on the bead in the directions shown in the diagram. The magnitude of the resultant of the three forces is Rn in the direction shown in the diagram. Find the values of F and R. Well, we can resolve the forces horizontally and vertically. Let's just see how it works. So all the forces acting horizontally would be to the right, we have F cos 70, and we have a 20 acting directly to the right. And we have a force acting to the left, that's 10 cos 30, and that should be equal to the resultant force acting to the right, and that's R cos 15 degree. And the forces in the vertical direction, we have 10 sine 30 degree acting downwards, and we have F sine 70 degree acting upwards, and that will be equal to the resultant force acting downwards, R sine 15. And now you have a simultaneous equation, a set of two equations and two unknowns, which means you can solve it to give you F equals 1.9 Newton and R equals 12.4 Newton. So now solved for the forces, we want to know if initially the bead is at rest at A, it reaches B with speed of 11.7 meters per second. Find the mass of the bead. Well, let's just apply Suva to this particle again. We'll use the equation v squared equals u squared plus 2as, because we don't know anything about the time, but we do know something about the initial velocity, the final velocity, and the distance. So we know that the final speed is 11.7 squared is equal to 0 squared, because it's initially at rest, plus 2 times acceleration times the distance, which in the question it says it's 30 meters. And wait, sorry, it says 3 meters. Solve that, you have A equals 22.815. So we now use again F equals ma, but we need to take extra care because only the force acting in the direction of travel is going to have effect in this equation, which means it's the component of R parallel to the line AB. So R cos 15 would be equal to M. times the acceleration. And plug the value of r in, we'll get m equals 2.6. Question 6. A particle P moves in a straight line starting from a point O. The velocity of P, measured in meters per second at time t after leaving O, is given by this equation, equals 0.6t minus 0.03t squared. So it's quadratic with negative coefficient of t squared. So it's going to look something like that. So the speed is going to have a maximum. And we're going to investigate about that later in the question. So verify that when the particle is 6.25 meters from O, find the acceleration of the particle at this time. Well, how do we go from a function of time that represents the velocity to a function of time that represents displacement? Well, we know that v is equal to ds by dt, and in order to find s, we can integrate both sides of the equation. So we'll just swap around. We have s is equal to the integral of v dt. So s is equal to integral of 0.6t minus 0.03t squared dt, and that's 0.3t squared minus 0.01t cubed, and we'll have a constant of integration c flying around. And we know that when t equals 0, the particle is at the origin. So c must be 0 as well. So you can just get rid of the integration constant. In order to find a from v, we know that a is equal to d2s by dt squared, which is just dv by dt. And if we differentiate the expression we had from the question, we'll get 0.6 minus 0.06t. So let's just plug in some numbers. When t equals 5, the displacement s of 5 will be equal to 6.25, as the same as the question. And a would be equal to 0.6 minus 0.01 times 5. That gives you 0.3 meters per second squared. In the second part of the question, we're asked to find the values of t at which the particle is traveling at half of its maximum velocity. In order to find the maximum velocity, we need to do differentiation. So find the stationary points of the function v equals 0.6t minus 0.03t squared. Differentiate that. A is equal to 0.6 minus 0.06t. So a is equal to 0 when t is equal to 10. So plug t equals to 10 back to the equation for v. We'll know that v max is equal to 0.6 times 10 minus 0.03 times 10 squared, and they'll give you 3 meters per second. And we now use the equation that 0.6t minus 0.03t squared is equal to half of the maximum velocity. So that's 1.5. And that will give you a second order equation in t. And after solving this equation, you'll find that t is 2.93 or 707. Question 7. A cyclist starts from rest at point A and moves in a straight line with acceleration 0.5 meter per second for a distance of 36 meters. The cyclist then travels at constant speed for 25 seconds before slowing down, with constant deceleration to come to rest at point B. The distance AB is 210 meters. The first part of question 7 is asking to find the total time that the cyclist takes to travel from A to B. Well, the cyclist is traveling at various different speeds in the distance AB, so we need to look at different segments of the travel separately. So first, we have the bit where the cyclist is accelerating at the rate 0.5 meters per second for 36 meters. So we have a super situation. We can use that S is equal to ut plus a half at squared to find t. So 36 is equal to 0 plus 0.5 times 0.5 t squared. And that will give you t equals 12. After the time travels at constant speed for 25 seconds, so this is the first one, we'll just have t2 as t1 equals 25 seconds. And the last bit where we want to know how much of the 210 meters are left with. So we work out the final velocity of the cyclist at the end of his acceleration. V equals 0 plus at, that give you 6 meters per second. So 210 minus 36 minus 6 times 225, they'll give you 24. And the 24 is traveled while the cyclist is decelerating. So we know the final speed and the initial speed. So 24 is just equal to 6 plus 0 divided by 2 times t. That'll give you t equals 8. And you add all these times together, you'll just have the final time. Total time is 45 seconds. Now we're told 24 seconds after the cyclist leave point A, a car starts from rest from point A with constant acceleration 4 meters per second towards B. It is given that the car overtakes the cyclist while the cyclist is moving with constant speed. So if the cyclist is moving with constant speed, the time must be greater than 12 seconds because that's it's between 12 seconds and 37 seconds of the travel of cyclist, the speed is constant. Find the time that it takes from when the cyclist starts until the car overtakes her. Well, let's set up an equation. Let's just suppose you take time t. Suppose take time t. So distance traveled by the cyclist can be written as 36 plus 6 times t minus 12, because we're assuming that the cyclist is still traveling at constant speed when the car overtakes her. That will be equal to the distance traveled by the car. That will be 0.5 times 4 t minus 24 squared. Well, this is now a quadratic in t, and solve that to be t equals 33 or t is equal to 18. And we shall see that it only works when t is equal to 33 seconds, because if t is equal to 18, the car hasn't even started yet, because the car only starts 24 seconds after the departure of the cyclist. So we need to choose the right answer. So that's the end of the paper.